0 and 1, but I think I'm wrong.
Okay, let's come to order. Like I said, I wanted to let you struggle a little bit on the warm up here. I think that's been 15 minutes though, so I think we're gonna call it. Okay. Yeah. That was 15 minutes. So let's call it. I know that some of you, made more progress than others, but so I hate to give away the answer, but let's see if we can systematically go through this. Hopefully, at the very least, you've tackled the first one, and I won't be like giving too much of the answer away by doing this with you right now. So this is a very interesting function, and some of you already looked at it, maybe on your calculator or whatever, and you've realized that this thing is not like your run-of-the-mill function. There's some interesting things going on. But it is, we can subject it to the first and second derivative tests, or the first derivative test, I guess, is all we're doing here. So the first derivative is maybe a little bit of a task in itself to get. So let's think hard about that. We got maybe a product rule to think about first, times the derivative of the second. What's the derivative of the second thing? That times, what is that? X to the negative first, so negative x to the negative second. All right, so first times the derivative of the second plus second times the derivative of the first. I have like an e to the 1 over x. I might factor out just for fun. I don't know. Irresistible to do that. So I have like a negative 1 over x plus 1. And now I seek places where the derivative is either undefined or 0. Remember, we're looking for both. So I think those places are when x is 0, it's undefined, right? And then the places where this thing is 0, where is this 0? Well, it's certainly this. Can you convince yourself that e to the 1 over x, and you might think, if you're going back to your thoughts about factoring in life, right? Right, something times something equals 0. Well, maybe this thing could be 0. Is it possible that e to the 1 over x could be 0? I think e to the whatever you like couldn't be 0, right? No matter, even if it's, e to the anything, no matter what crazy that could be, that definitely can't be 0. So I don't need to worry about that. But this could be 0. Maybe just even by inspection you can tell me when that happens. When x is 1, yeah. So I think we've got them. That might have been a little bit of a task for people out there, just that, right? For coming up with those two critical points, 0 and 1. Okay, great.
Yeah.
What's that? You good? Okay, so 0, we'll put them in order on a number line. And remember, we're thinking about y prime. A couple people as I walked around told me, I keep doing this. On the homework, I was doing this too. I plug my my points in between into the original function or whatever. Yeah, make sure you're plugging these into the derivative. I'll just make sure to do that by putting a y prime here to remind me. If I plug in values to the left of 0, like negative 50 or something like that, again, this will be positive, so this doesn't even have to be in the picture as far as I'm concerned. This will be something positive. It always will. I said that. If we're plugging in negative 50, this will be 1 over 50 plus 1. It'll be positive. So this is positive, I think. That is the derivative. Y prime is positive here. And then in between, if you plug in like 1/2, again, this will always be positive. I'm just really concerned about this. What's going on there? 1 over 1/2, that'll be 2. Oh wait, negative 2 plus 1 is negative 1. It's something negative. And then after 1, if you plug in something like 1,000,000, you get something positive here. You get negative 1 over 1,000,000 plus 1 will be positive, won't it? So did you get that too? So at the very least, we can say that this function y increases, decreases, and then increases. And then someone want to help me out here with kind of the nuanced interpretation about this piece. We haven't actually done this yet. So why is that a little bit actually not so easy? Yeah, Albert?
It's not easy, I know it's wrong.
Okay. Do you want to be like do you want to walk into the trap though? Go ahead.
I'll go for it.
Go for it.
Because it's increasing, it's positive before 0.
Yep.
That means that the slope is positive, and
You got
when
it.
it is negative, that can kind of imply that it's max at 0.
Okay.
And then when it goes from the slope goes from negative to positive.
Yes.
At 1, we can imply that it's a minimum.
Yeah, decreasing and then increasing. So that's a min. Yeah. All right, and then what's the only catch there? Someone want to say, Steven? Yeah, the original function isn't defined at 0. The original function isn't even defined at 0. So we maybe need to like make sure that that makes sense to us, like if you actually plug it in. But we do have one minimum on this function, only one, local minimum, and it's at 1, comma, e. And if you haven't done so already, let me show you the graph of that, just so you can actually, is this right? I mean, how could that happen, you might say, right? How is that possible? So here's the graph of this function. And this point right here, there it is. Let's click on it. 1 comma e, right? Beautiful. So what's going on there? Well, there's this vertical asymptote on the original graph, right? Huh? Yeah, it's kind of crashing in here. What might you guess the limit from the left? It's not, if you plug in 0 to this function, you get nothing. It's undefined. We already established that. But it sure looks like the value wants to be 0, at least the left side, right? So I might say we could actually, I don't know that we actually have like the algebraic, without looking at the picture, if I just ask you to look at that, the limit as x goes to 0 from the left of x e to the 1 over x, apparently it's 0. You might have to convince yourself of that algebraically. I mean, the picture seems to indicate that though. So that's a little tricky. But I think we did it. Was it increasing, and then decreasing, and then increasing? It sure was. Yeah. Great. So that's nothing more to say about that. But I think I don't want to trivialize that problem. That's tricky, right? That's not easy. Okay. And then down here, I don't know about you, but unless you have a desire to keep seeing it in that way, I might multiply this out. I don't know. Is that okay? I don't know. And then now I can just use the power rule twice, right? So y prime is what? 4/3 x to the 1/3, right? Minus 4/3 x to the negative 2/3. And y double prime we need 2, right? So is that 4/9 x to the negative 2/3. Oh my, 8/9 x to the negative 5/3. Yeah? Alright, so then we seek places where the second derivative now, we're trying to test for points of inflection and concave up, concave down intervals. So again, we need kind of the critical points of the second derivative. So one that should be somewhat clear to us maybe is what? 0 is undefined for, right? So we can write that one down like right away if you like. It makes both of these two power function monomials undefined. So 0 is one of them, for sure. And then now the other task though is to ask, is this ever 0? And that's actually, that itself is like, even you think, could I outsource the algebra to like my pre-calculus friend? I don't know. I mean, even the pre-calculus version of yourself might struggle with this, right? We're not doing calculus right now. We're just asking, what is the solution to that equation? It's not obvious how to go about solving that. Did you have a method you want to suggest? I have like 2 ways of working it on my paper that I did. But yeah, Kathy, you got a good way in, huh? Yeah. Okay. Great. So how did you factor that? I mean, this is not the type of factoring I'm used to, maybe. So. Sorry, say it again. 4/9 x to the. Okay. Times x plus 2. Verify that she's right by multiplying it back out. Does it work? By the way, if you already know that it's undefined at 0, you could actually do the thing that like we kind of say. This is the second way I worked it out off to the side. I did it Kathy's way, but then also off to the side, I also said, okay, well, if I move one of these expressions to the other side, and then like multiply by various things, then you do get pretty quickly. You get -2. I got like x cubed equals -8, and then I'm like, oh, x is -2. Usually we're a little cautious about that because we know we can like lose solutions that way or whatever, but as long as you're careful and you like understand what you're doing, that'll work too. One way or another, you do need to see that x equals -2 is the other critical point we're looking for. Okay, so let's put those on a number line. And then we're testing, again, let's go back to the second derivative here. Maybe in this form down here that Kathy has it. And put values in. Let's see, if we put in negative a million or something, what do we get? What will that be? Well, that'll be something negative, won't it? Okay, so that's negative times something negative is something positive. And then if we plug in a value like -1, we'll get something negative times something positive. So that's negative. And again, we're talking here about y double prime, in case anyone's not clear on that. And then if you plug in a value greater than 0, like 1, you'll get something positive, won't you? But again, I don't want to rush you too much here. This is each one of those thoughts is kind of heavy along the way here. There's a lot of mess happening. Great. So then our conclusion is what here? The original function y is, if the second derivative is positive, it's concave up, concave down, concave up. And assuming the original function, is the original function defined at both of these places? I think it is. So, so I think we can safely say these both are points of inflection. Did I give the y coordinates? Yeah, I think I did. I went all out here. Okay, so I said up here, I said min at this. And here, I'll find some room over here. How about, I wrote it's concave up on negative infinity to -2 and 0 to infinity, open intervals. It's concave down on the other interval. And we have points of inflection. I didn't give the y coordinates, -2 and 0. But there's the summary of what we're looking for, I guess. What did it say? And all points of inflection. You could plug them in if you were cooler than me. But, all right, so that's quite a warm-up, right? Are you warm? Do we need more? That was a great use of time, I thought. Okay, let me. Do you still need that for a second? Sorry. Or do you still need that for a second? Or you do, Marcus? Okay. My goal is just to say some more about the first and second derivative of it today here. We already have. Talk about curve sketching a little bit. You good, Marcus?
I'm good.
Okay. Yeah. Okay. I think this is where we left off, somewhere in here. Yeah, right here. We were talking about how to do this. I think we did this over on the board. We determined where this function right here, this cubic, was increasing and decreasing, mins, maxes, concave up, concave down, points of inflection. And hopefully this was like the easy example of that. After seeing the warm-up, you can see that we can make these harder. Okay. So this is a nice easy example that kind of confirms our pre-calculus notions of what that graph should look like. Keeping with that in mind, let's actually maybe think about how to graph these things too. I don't know if the homework invited you to do that at all, but I'd like to invite you to do that. It will. And really, as we think about the first and the second derivative, there's only 4 pictures we can have. Here's the first one, right? And what's going on there? The first derivative is positive, and the second derivative is negative. So that's that picture. I'll show you the other ones here. So the first one is what you said. What about here? First derivative is positive, second derivative is positive. What about in this picture? First derivative is negative, and second derivative is, which is it? Is it part of a frowny face or a smiley face? It's a frowny face, yeah. So that's the second derivative is negative, and then the last one, first derivative is negative, and the second derivative is positive. And again, I think yesterday we talked about this, and we said, how can there be anything negative about this first graph, for example? And we talked about with the calculus mindset, yeah, there is something that's decreasing about that graph. Its rate of increase is decreasing, right? Well, same thing here. Someone might look at that and be like, how can you say anything positive about that graph? That's not very nice. But things are looking up for this graph. In fact, if it continued, if you were allowed to continue, then we'd be able to see it turn up a little bit, right? So, right? It is absolutely true that the derivative is increasing on this graph as you go from left to right. Just calculate the slopes. You'll see -5, -4, -3. Oh, they are going up. -2, -1, 0. 0 is better than -4, you know. So that's good. That's good. We're getting better. So I just wanted that's our arsenal, right? So as we go to graph this, we want to kind of piece. Those are the 4 puzzle pieces of our picture that we're going to draw. This is the same example we had a minute ago. So I'm trying to think whether we had. Do you have it in mind here? Let's see. We got a min and a max and a point of inflection. Can you tell me where they were? I can go back to that slide, but I thought.
Max at 0, min at 2,
At 1? Okay. So I might actually do this on here. 0, 1, and 2. So these are not asymptotes, just to be clear. I just want to kind of partition the graph into 4 pieces. Okay. So in each of these sections, the first derivative is all positive or it's all negative, and the second derivative is either all positive or all negative. And so in each piece of this graph, I'm going to use one of those 4 pictures to construct this, right? Those 4 pictures on the last slide. And we'll get the whole picture of this. Again, keep in mind from your pre-calculus knowledge, you already know what this looks like for the most part. So it should hopefully just confirm what we said. So maybe I'll actually even put the number lines up here too, just so we have them. Y prime and Y double prime. 1, 0, and 2, just to make this really clear here. It went from Y prime was positive, and then negative, and then positive. And Y double prime was negative and then positive. I'm just copying the stuff I had on the board the other day, right? Yesterday. Great. So what about on the interval -infinity to 0? The derivative is positive, right? And the second derivative is negative, right? So that is, it's increasing, but it's concave down. So there's one of the pictures we graphed earlier that looks like that. It's got this shape, right? On this interval. And then what about on the next little sliver of an interval? Now, that is from 0 to 1. From 0 to 1, the first derivative is negative. The second derivative is also negative. So which piece was that? Looks like this, doesn't it? Has this shape. I'll draw a little in there. And then the next interval, this first derivative is still negative, but the second derivative is now positive. So we get this kind of shape in here. And then in the last part, we have both are positive. We've got this shape. So actually, right here, we see all 4 pictures, don't we, in some order or another. Great. Now, before we actually go to draw this, let's anchor it with some points. I've got a couple. If you plug in 0, it's 4. 1, 2. Here, let's do this in another color just to make this clear. 0, 4 on there. 2, 3, 4. It's factored for me, so I might use that to my advantage to try and draw this nicely. 2, 1, 2. We found that there was a minimum at 2, a max at 0, so those actually correspond to the max and the min. And the point of inflection was at 1. Let me just go. Do you have an idea what that is? Maybe it might be 2. Let's plug it in and see. If you plug 1 in, do you get 2? All right, good. All right, good. And we already, like I said, with pre-calculus knowledge, you would have had a good graph of this too on this one. But does this look like that? Is this a picture of a graph that's increasing and concave down? Yeah. And then in this little section here, a graph of that shape where it's decreasing and concave down. And then a picture that has us decreasing but concave up. And then a picture after that of us increasing and concave up. So I mean, a cubic graph, literally is made of kind of 2 pieces like this, right? Isn't it? Where my fingers meet, we have the point of inflection, right? I guess this perspective for this one. There it is, point of inflection. So again, a lot of calculus power for a pre-calculus problem, but I thought it's good to look at this in this smaller context. I mean, really, it really is only those 4 pieces. So as you graph this problem, I haven't given you any function to go with this. I'm just telling you, I'm just giving you the sign charts. Can you give me a reasonable picture of this? Again, here's your like kind of arsenal of things you can use. I intentionally overlap these in a way that's helpful, I think. Yes. You don't need to know what the function. And by the way, all of us will have anchored it slightly differently, right? We also have like a feel for what this looks like, I think. I like some random things I'm giving you, okay? Just for fun. Eventually I might refer to one of them, but these are not home. These are not home. They're not home. Like the thing I just passed you is kind of a helpful summary of some of the things that are it's really just photocopied from the book, correct? But useful enough that you might want it as a reference. It really is just photocopy. You could have made it yourself.
Oh, wow.
I think on the homework thing on the first slide, you need more.
Wait, you guys did this?
I think on the homework, on the slide, on the first slide, it said you should do homework for tonight, and also this, I think. Right? Didn't it say the first derivative word bank worksheet? Okay. The other worksheets I'm not asking you to do here. All right, so let's see if we can graph this here. I'm going to do kind of the same thing I did before, right? I got 0, I got 2, I got 3, and now I'm going to try and figure out what this looks like in each interval, right? So here it's decreasing but concave up, decreasing but concave up, decreasing but concave down, decreasing, concave up, and then increasing. So I think we have this kind of shape, right? So maybe something like this. I don't know. You could interpret this in a couple ways. Something like that, right? Feel good? Yeah. The only thing that goes with homework 4 from the book is this word bank one. Yeah. Okay, you could like do that now in a few seconds. It's pretty quick. It's just there's no calculations to do. It's just, let me yeah, the homework is homework 4 plus that word bank worksheet. Let me make sure that I did say that. Yeah, the word bank first and second derivative. Actually, well, I guess I meant to give you this one too. I'll give you this one tomorrow. You already have enough stuff. Like I said, I mean, some people are already like receiving completed here. It really shouldn't take too long to do the word bank thing. Everyone get a clear message? You got it. And I promise I'll fix your 2 out of 12, okay? People out there.